All right, guys, today we're going to be talking about calculating the electric potential from some source charge or set of source charges. But before we get to the new calculations, I just want to go back over very briefly what we talked about yesterday, because I know yesterday was a lot, learning about potential and potential energy and conservation of energy, all sorts of crazy stuff. So I just want to go over the key points once again. So the big thing we learned is that every point in space has a quality called potential, and this potential is a quality of the space itself, not something in the space, of the space itself, and it's a scalar. It's just a number. Now, if you place a charge in an area that has potential, it gets potential energy. So the potential energy is a property of the charge once you put it in that space. And this little equation over here is how you would calculate the potential energy from the potential. Potential energy is U, potential is V. And the potential energy gained can be calculated by finding the work done on a charge to move it to that point. And we're going to see that today in our lesson. The third thing is that charge moves between points if they have a potential difference. And the formula for potential difference is right here. Now, a weird thing that happens with electricity or electric charges is that positive particles move from high potential to low potential, but negative particles act opposite of that. They move from a low potential to a high potential. And the last thing is that a particle's total energy is conserved, which is essentially saying kinetic plus potential at the end has to equal kinetic plus potential at the beginning. You can't have more energy than before unless work has been done on the system, which would add potential or kinetic energy. And that can be summarized in these two equations there. So really, potential and potential energy is just an energy formulation of the same ideas that we were learning before about forces and fields. It's just approaching it from an energy standpoint rather than a forces standpoint. So now that we know what potential is, we kind of have to learn how to calculate potential and figure out what the potential in a space is. And potential can be defined similarly to electric field from force. Potential is simply the ratio of the potential energy to the charge. And the charge that we're referring to here is the charge you put in the space of potential, not the charge generating the potential. So, for example, if we had a source charge here that is radiating a field, and there is potential at every point, Q is going to be the charge we put in that space. That's the Q that's here, not the Q from the source charge. So to find potential, we have to know the potential energy, and to find the potential energy, we have to find the work done on the particle to move it there. So work is change in potential energy, and we can calculate that in some scenarios because work is also equal to force times the distance, which is sometimes a straightforward calculation, sometimes it's not. We'll see what it looks like here in a second. So let's look at a parallel plate capacitor. Parallel plate capacitor is two parallel plates, shocker, I know, that are oppositely charged. So one side is going to be positive and one side is going to be negative. Now we should know from the last chapter that a parallel plate capacitor generates a uniform electric field that points from the positive plate to the negative plate. And we had a formula or an equation to calculate that field, and it was that the field equals the total charge on one of the plates divided by epsilon naught, which is the permittivity of free space or vacuum permittivity, times the area of one plate. And that's how we calculated the electric field, which is of the same direction and magnitude everywhere inside the capacitor. And we also know from last chapter that the force on a particle Q is equal to the electric field times the charge of that particle. So if we want to calculate the potential somewhere inside this capacitor, we'll have to know the potential energy of a charge at that point, and then divide by the charge. And to get potential energy, we have to know how much work would be done on the charge to put it at that point. So we're going to need this force to calculate that. I'm going to shrink this a little bit so I've got some more room to derive, because that's what we always need, is more room to derive. And we'll start with the equation work equals force times distance, or displacement, whatever. And if you're keeping up with scalars and vectors kind of thing, this is a dot product, which the dot product of two vectors becomes a scalar, so work is a scalar. If that made no sense to you, don't worry about it. Not really something you need to know, just some fun facts I'm throwing in. So in this situation, the force is going to be the field times Q. So we're going to go ahead and substitute that in. The work done on a particle, if we're moving around inside the capacitor, is the field of the capacitor times the charge of the particle we're working with times the distance that particle is moved. And if we want to substitute even further, we could say that work equals the field, and we'll substitute in this expression for field. We'll do charge on the plate divided by permittivity of free space times area times Q of the charge. We'll go ahead and draw the charge in there, random charge. Times Q of the charge in there times D, which is the distance the charge moves. So before we go any further, we need to kind of better define this D for distance or displacement, and kind of look at what we're doing with the particle inside the capacitor. So we're going to assume a positive test particle, because that's usually what convention states. So we're going to make this a positive particle. Now, if we want the particle to have the most potential energy, we're going to have to push it towards the positive plate, because that's where it would have the most potential. So we want to make our zero, the starting point, where it has the lowest potential energy, the negative plate. So we're going to make the charge start off at 0. We'll push it towards the left, towards the positive plate, and figure out the potential after we've been pushing it that direction to the left. Now, another note, which we did cover last time, is that you can set the 0 to be anywhere. It's arbitrary, that's fine. You'll just add or subtract from that 0 point. So this D, this distance or displacement, is going to be the distance from the starting point of 0 potential to however far we push it to the left. So from before, we know that work equals force times distance, which we have computed here. But work is also equal to the change in potential energy. So we can rewrite this expression, or this equation, as Q over epsilon naught A QD equals delta U. And from there, it's a very simple matter to calculate the change in voltage, or the potential difference, because we have another equation that states that the difference in potential is equal to the difference in potential energy divided by Q. So to get potential energy, we just got to divide this whole equation by Q. So if you divide this side by Q, you get delta V. If you divide this side by Q, these Q's cancel, and you get that the voltage across a capacitor is the charge on one of the plates times the distance across the capacitor, or however far you've moved inside the capacitor, over epsilon naught times the area, which is a standard formula that's used lots of places, but we have now derived it. Now this equation is commonly left in a different form, where instead of putting Q over epsilon naught times A, we leave it in the form of electric field. and you say electric field equals delta V over D. This, I guess, iteration of the equation can be easier to use when you're just looking at the potential difference across the capacitor and you need to find the electric field. So when you're inside the capacitor itself and you haven't gone all the way across, but you know the potential difference across the entire capacitor, you can just use a proportion to solve for the potential difference across 2 points instead of across the full capacitor. So let's look at an example of this. I'm going to have capacitor plates. Let's see, I'll make this side positive this time, and the other side negative. And this has got some distance across D, but we want to know the potential difference between 0 at the negative plate and, let's say, this is X. Okay. We want to know the potential difference between the plate, the negative plate, and somewhere on this line. We'll just call the point here. So to find the potential difference across those 2 points, you just have to do a proportion. And the proportion says this potential difference that you're searching for out of the total potential difference, which is the potential difference of the capacitor, equals the distance you went, X, over the total distance, the capacitor, D. So if you solve this for your potential difference that is in question, I'm going to put it as a little question mark, you get the potential difference you're looking for is X, your position, times the potential difference of the capacitor divided by D, which is the same thing that's right there. So one of the consequences of that we just looked at is that a parallel plate capacitor's equipotential surfaces look like this picture. So an equipotential surface is just a surface, two-dimensional thing, that has equal potential. So in a capacitor, after you go across a certain distance, every point that is that distance from the plate, which would form an imaginary square surface, has the same potential. So everything on that square has this potential, everything on the next square has that potential, so on and so forth. And you could have infinite squares inside the capacitor. And mind you, these are imaginary things that we have created in our minds to help us calculate things. They do not physically exist. All right, so before we move on to point charges, we're going to look at a specific example with a capacitor. It says a parallel plate capacitor is constructed of 2 discs placed 2 millimeters apart. So we're going to look at 2 discs, disc and a disc, and the distance between them is 2 millimeters. 2 millimeters is 2 times 10 to the negative third meters. It's charged to a potential difference of 500 volts. So I'm going to say this plate's negative, this plate's positive. I'm going to make this plate 0, so if there's a potential difference, this side has to be 500 volts. A proton is shot through a small hole in the negative plate with a speed of 2.0 times 10 to the 5th. So we're going to have a proton shoot across that way. Speed is 2.0 times 10 to the 5th meters per second. Because to complicate matters, we have to have both a V for velocity and a V for potential and a V for the unit volts, all in the same scenario. And the question says, what is the farthest distance from the negative plate that the proton reaches? And if you think about it, this makes sense because a proton likes to go from somewhere with a low potential to somewhere with a high potential. So basically, it would be like throwing this proton upwards and it's slowing down, and we're going to try to find its highest point, the point it gets furthest in its trajectory. And we can do that using conservation of energy. So conservation of energy says at the beginning, right when it goes through the plate, the potential of the particle, or the potential energy, is Q times V. And V here is 0. So Q times V is 0. So at the beginning, it's got all kinetic energy, which is 1/2 mass times velocity squared. So you would do 1/2 times mass, and this is a proton, so it's whatever the mass of a proton is. That's just a constant you can look up, times velocity 2.0 times 10 to the 5th meters per second squared. That's the kinetic energy at the beginning, and that's the total energy, because at the beginning there is no potential energy. And then at its furthest point, that's going to be right where it stops. The kinetic energy is going to be 0, and it's going to have 100% potential energy. So this 1/2 mv squared is going to be equal to the potential energy of the charge at its highest point. So that's equal to U. Now we know that if you divide U by the charge of the particle, you get the potential. So if we divide this number by the charge of a proton, 1.602 times 10 to the negative 19, divided by charge of proton, you get the voltage, so, or the potential. So we would find some number for potential using this calculation. I'm not actually going to calculate it out because I don't really feel like it. It's late at night and you can number crunch yourself. But that would get you some number V. So pause the video now, come up with that number, write down that it's V. And to figure out the distance that the proton reaches, you take that V and figure out how far between 0 and 500 it is. So you do V out of 500, solve it like a proportion, that equals the furthest distance x out of the total distance between capacitors, which was 2 millimeters. So you would solve this proportion for x using the V value you had down here. And that would tell you the furthest distance from the negative plate that the proton reaches. You would also be able to calculate this from force and kinematics, but this approach with energy or potential is a lot simpler, a lot cleaner, and just involves less calculation. All right, so moving on to the electric potential of a point charge. I'm going to minimize this slide real quick just so we can talk about a couple of things, and then I'll get back to it. So if you think about a point charge, it's got a field going like this, and as you get further away, the field gets smaller. And that's because the force decreases as distance increases. I'm not going to draw out the whole field. You get the point. Force decreases as distance increases. So if we needed to calculate the work used to give a particle potential energy, say we have a particle that's positive, particle Q, and we want to give it potential energy by pushing it closer to this particle. To do work, we'd have to calculate force times distance, same as before. However, as you approach the positive charge, this force is constantly changing based on your radius. So it's not a straightforward calculation algebraically. It actually involves integration and calculus. So it's not within the mathematical scope of this class. So rather than deriving this formula for the electric potential of a point charge, wait till you get to calculus-based physics to do that, and just believe me that the potential follows these formulas that I'm about to present to you. All right, so here they are again. The top one is about the electric potential energy of a point charge based on a source charge. So in these equations up top, Q without the prime is the source charge, and Q with the prime is what we'll call the measurement charge. It's the charge we're observing. So to find the potential energy of some charge due to a different source charge, you just plug and chug into this equation, 1 over 4 pi epsilon naught, Q1, Q2 over R. Simple as that, just plug it in. And to find the voltage or potential difference between 2 points of in the field around a point charge. You calculate the potential for each point using this formula down here. It's the same formula as the top. It's just divided by the measurement charge so that the measurement charge becomes irrelevant and we're only looking at the space. So really with these formulas, no derivation, not a whole lot of thinking, just plug and chug. But I am going to ask you a little conceptual question, and it's about what equipotential surfaces for the area surrounding a point charge would look like. And for that, we'll need the formula still. So we get that the potential is K, which is a constant, times Q, the charge of the source charge, over R. So this varies, means the potential varies based on the radius, and it's 1 over the radius that changes. So as you get further away from a point charge, the potential is going to decrease. And it's going to decrease kind of in a manner like this, because it's a rational function, 1 over r. Okay, so it decreases pretty rapidly at first, and as you get further away, the slope decreases, and it decreases less rapidly, which was a lot of words all at once. Anyways, so the equipotential surfaces are those surfaces where r is constant, which is a sphere. So that would look like this. Here is a graph of the potential based on r. So every surface that has constant r, which is a sphere, has equal potential. All right, now to calculate the potential around a point charge. Super easy. We're going to use that same formula. Potential equals K. I'm going to leave things in terms of K times the source charge over the radius, or how far you are from the source charge. So looking at the question, it asks, what is the electric potential 1 centimeter from a 1 nanocoulomb charge? So it's pretty simple. Potential, V, equals K. I'm going to leave it in terms of K. Times Q, 1.0 times 10 to the negative 9th. And that's coulombs, over R. 1 centimeter is 0.01 meters. So your potential is whatever that number is. Then it asks, what is the potential difference between a point 1 centimeter away and a second point 3 centimeters away? So we already have the potential at 1 centimeters away. Now let's find it at 3 centimeters away. Potential equals K times the same charge, 1.0 times 10 to the negative 9th coulombs, over 3 centimeters is 0.03 meters. So this is the potential at point, we'll say 1, and at point 2. Now to find the difference, all you got to do is subtract. V2 minus V1 equals 9 times 10 to the 9 is K, times 1.0 times 10 to the negative 9 coulombs. Let's see, I should probably include units for K, which is newtons times meters squared over coulombs squared, divided by 0.01 meters. Sorry, V2 is 0.03 meters. 0.03 meters minus the same thing, 9 times 10 to the 9. I'm going to leave out the units because I don't have space, but I should write them, times 1 nanocoulomb over 0.01 meters. And you can do the number crunching for yourself. But that's how you would find potential and potential difference surrounding a point charge. All right, hopefully this was a little bit more concrete and conceptually easier than yesterday. We're kind of throwing around the words potential and potential energy a lot. Hopefully you know what they mean. If you don't, please email me and get some help, because they are different. You do have to know the difference. But yeah, hopefully this lecture was helpful for you, and you can calculate these things with no problem.